Hello everyone, my name is Zoey Ballard, and today I'll be presenting you how to determine the value of soft exteriors, robotic hands, and prosthetics using through user interviews. My name is Zoey Ballard again, and I'm from the University of Houston. And this summer, I did all this research through the Robotics Institute Summer Scholars Program at the Foam Robotics Lab here at Carnegie Mellon University. So let's get started. To kind of begin, I'll start off by providing some background of just like, what is the current state of prosthetics? Like, where is prosthetics currently at? A lot of prosthetics that you can see today on market usually include rigid designs that are capable of so many dexterous qualities that a lot of devices previously have not been able to do. For example, you can see the Tasca hand here, holding small objects like a pearl, as well as the Shadow Robotics dexterous hand, which is capable of holding like a light bulb, these delicate objects sensitively without breakage. And a lot of these hands that you can see on market now have been able to have these innovations due to the rise in robotics technologies, as well as artificial intelligence and other cognitive technologies, allowing to do these complex algorithms, as well as detections of force, etc., to make a more sophisticated prosthetic. However, a lot of these prosthetic hands still fall short of completing daily tasks. For example, our end user Brett kind of specified a lot of struggles that he experiences on a day-to-day basis with his own prosthetics. Some of which include just simply picking up a pencil. It can be very difficult and take several attempts to properly get done, simply because since most prosthetics mainly specialize in doing a 3-jaw chuck, just moving the first two and thumb finger, it can be very difficult to position properly to pick up a pencil and other thin objects like that. He also experiences difficulty trying to pick up a breathing tube. And as his job as a nurse anesthetist, inserting a breathing tube into patients is a key part of his job that he has to do on a regular basis. But it can be difficult to pick up this kind of thin breathing tube that he has to use the thicker end of it. And a lot of times he ends up just positioning it himself, trying to do that just to make his life easier using his able hand. But of course, a lot of people don't usually have this option due to the fact they may have 2 remaining limbs, so then they cannot actually use their able hand to position or need the help of other people. So their prosthetic is not very reliable in this. So then, of course, from these videos, this led us to conclude that a lot of prosthetics tend to struggle with like this kind of snatching or even picking grasp, which is just grasping objects off a table, specifically thin objects like pins, as well as that breathing tube. And also, even though we didn't get many videos of this, the prosthetics struggle with doing a screwing motion due to issues with having adduction, abduction properties, and only just having flexion extension, which later I will show a diagram to further explain this. But basically moving either right to left, which is adduction above adduction, versus extension flexion, which is just moving your fingers in and out towards the palm. Most prosthetics are only able to do that extension flexion kind of movement. They're not able to do the adduction abduction, which is typically what is done in screwing. And because prosthetics aren't able to do this, users like Brett end up taking off the prosthetic and using the remaining limb to turn a knob versus using their prosthetic, because it's a lot more reliable just to use the remaining limb. But then it means the prosthetic is not as valuable of a technology as it could be. Another thing that prosthetics struggle with that is not as clearly outlined is the fact that since it's rigid, it can have a lot of issues with fragility. Banging it into a table can mean a lot of times that the prosthetic can break over time, and it requires prosthetic users to replace their fingers and other parts of the prosthetic regularly just to make sure it can be maintained, because this breakage is very typical. So then the question is, with our in the foam robotics lab, we have a soft hand that we currently use. But then how exactly would this connect to prosthetics? So first, we'll start off by showing a lot of the capabilities of our hand. Our hand was developed by Dominic Bauer, Cornelia Bauer, as well as several others in our lab. And it's capable of doing these kind of like simple dexterous motions of just touching each fingertip. A lot of it because we have dexterity offered from these different tendons that allow these different movements that are very human-like. And also from previous soft hands that we've developed, you can see the varieties of objects that we're able to grasp, from thinner objects like a chip or an M&M, versus heavier, bigger objects like a drill. Though also first, let's demonstrate how we have these softness qualities that are very different from what is typically offered in prosthetics for the more rigid designs. Because we had this softness, we are able to have these collisions with objects and still maintain the same quality of our hand, as well as have no indication of damage from just banging it or smashing into a table as demonstrated in this video, which is a key quality that a lot of prosthetics don't offer. We also have a lot of dexterous motion, as demonstrated in this video, where we are grabbing objects out of a drawer. You can open the drawer with even just one finger and pick up these wide variety of objects out of the drawer. Easily, just slowly moving across each one and being able to specify which object, and especially because the hand is not rigid and able to collide with a lot of the different objects, it allows to have a better grasp on a lot of the objects, being able to wrap around them rather than having to adjust to slowly almost claw it out of the drawer. Even later in the video, you can see us picking up even small objects like that M&M off the table, and a chip, and even like a small pickle. So even our current hand is capable of picking up even small, tiny objects like an M&M or a chip, and even able to position the drawer back into its compartment. And again, here's kind of a diagram showing that a lot of that dexterity that we're able to accomplish is because in addition to having the hyper extension, and flexion that typical prosthetics offer, we have these adduction qualities, at least in a few of our fingers and eventually to all our fingers, that allow us to achieve more dexterous motion than current prosthetics are able to do. Since they only curl inward, we are able to curl outward, make our fingers go outward as well as inward with the adduction properties, being able to achieve a wider variety of grasps more successfully and more humanly. We also have other videos of holding just simple little tennis ball and being able to shift it between a variety of positions because of the adduction of our hand. And you can even see it now demonstrated in these kind of variety of grasps and how we're able to achieve like these human-like motions and tests. In the next video also, you can see the user trying to grab the tennis ball or shake the tennis ball out of the grasp, showing even how much force we're able to exert despite the softness and being able to control these tasks. So from this video, it's clear that we have a lot of dexterity and softness offered in our hand. But the main thing that we want to see, especially because we want to try to aim our hand towards prosthetics, is talk with our users and talk with them about what exactly they want from our hand that can make our hand more successful and a more prototype and prosthetic that they would eventually want to use. And that would address the issues that their prosthetics have rather than just making a prosthetic and testing it out. We want to directly have that user conversation and user interaction to make the best possible product for them. So the first step in doing this process, especially in my own research, was taking the difficult tasks that our end user Brett outlined, like screwing, as well as the picking and snatching of objects, and seeing how capable our current soft robotic hand is able in succeeding and completing these tasks. We also wanted to use these videos of the demonstrations to collect user feedback by doing several user interviews, about 14 user interviews, to discuss and interact with users about their feedback on this and where our current progress is at, as well as the goals that we aim to complete. We also, from our last step, is kind of to create a physical, like low fidelity prototype to demonstrate and test our soft hand as a prosthetic and use the improvements based on the interviews that we previously completed from user feedback and try to make these adjustments to try to see what it could be as a prosthetic. And then eventually later take this prototype and bring them back to users and get more feedback of exactly what they believe our hand should be able to do, as well as future steps that we may want to consider taking. So first, of course, we started by completing these difficult tasks. I did a lot of this by hard coding motor positions from each motor is controlled on a variety from 0 to 1 and being just hard coding these poses into the hand, trying to ideally do it from only using 1 or 2 poses to be able to do either a simple screwing motion or a simple grasping motion. So as demonstrated here, you can see the simple screwing motion done only in about 2 poses, being able to turn this can with only like a few hours of just like working through the poses as well as just hard coding it in. It can easily turn the can quite reliably. And then later you can even see with the grasping object, we're trying to pick a thinner object like an expo marker off the table. Again, this was only done in just a couple of hours of just hard coding the position, but yet it can reliably grasp and pick the marker off the table. So from these demonstrations, you can even see that our hand is capable of achieving these more difficult and dexterous tasks that prosthetics are able to do. So we see this as a very hopeful future direction towards our end goal of creating that prosthetic for our users. Our second step, of course, was conducting these user interviews. We tried to make sure the layout of the user interviews had these introductions as well as the presentation and demonstration videos, which was kind of the videos shown earlier in this presentation, and then to demonstrate the softness, dexterity, as well as those turning and screwing motions to our users. But our main focus in the user interviews is to provide plenty of time for questions and feedback and to try to get as many ideas as we can regarding improvements that we can make to our design. We also decided to conclude by having a post-interview survey so that our users can directly tell us, even after the interview, ranking our softness and dexterity levels, as well as the innovation of our design on a scale of 1 to 7, with 1 being strongly disagree with the progress that we have, and 7 being strongly agree. Just being able to see, having some numerical data that we can analyze, as well as also provide a place that after the interview, users can provide additional feedback that they may have not said during the interview. So from there, from the interview results, this is specifically first looking at the survey, we were able to find that with the softness value, about 73% of users found that they did strongly agree that our softness that our hand offers could be incredibly innovative in current prototypes. And then with the dexterity, about 45% of users said that our current dexterity is going to be useful and innovative. And the overall value of the hand was around like 73%. They found that the innovations and additions that we've had through the softness and dexterity, as well as the capabilities of our hand, demonstrate something that could be valuable for prosthetic users. So overall, we found these results very encouraging, because they show kind of, even despite like we have a very early stage in our process, we only recently developed this hand 2 years ago, and we have only just started considering its applications as a prosthetic. We still are able to achieve a lot of these positive results with around 70 to 50, like majority of the users saying that our ideas right now demonstrate a strong completion of our future objectives of achieving this prosthetic. And we also had a lot of key feedback from the interviews that included creating more user customization, customizing the autonomy levels of the hand, either having highly user-controlled devices of, if, for example, a user wants to pick up a phone, they slowly control the hand in doing that, versus having assisted autonomy where you just hover over a phone or give a vocal command and then the phone gets picked up by the device. We also may consider doing more customization based on appearance, either having a more human-like design, maybe even having a soft-skin glove that they can put over it, versus having a more typical prosthetic or robotic looking design and even more customization on strength, as well as maybe having modularity. A lot of this was very emphasized in our interviews, something to consider to attract a wider cut variety of prosthetic users and be able to have them choose a device that best fits them. Because of course, every single user won't want the same thing out of the device. They may want something that's more task specific and want to even like switch out and have a wide variety of hands that are more customized to certain tasks. Or they may want to have a prosthetic that's more accustomed to doing a wide variety of tasks, and they would just want to use one single prosthetic. But again, these are all based on user preference. So it's important to have that customization, as we learned in the interviews. We also want to try to work for a more human-like design, having that more limited motion and the soft outer skin that kind of makes it look more human-like, especially because, as one of our interviewees pointed out, a lot of our world is custom made to work with human hands. So it is important to have that human-like quality in the hand to be able to manipulate objects, etc., and do daily tasks that are expecting a human hand to do. We also considered even adding some more failure detection, similar to how pain alerts us when we're about to possibly damage our own hand, having a failure detection to alert the user whenever they may come close to damaging the prosthetic or anything like that, which could improve the durability and reliability of our own hand. And also maybe conducting user testing for texture, softness, and general feel of the hand, since it will be interacting with people, and it should have that kind of aesthetic as well as softness and feel of material, so that people can feel comfortable interacting with this device on a regular basis. And people that aren't prosthetic users can feel comfortable interacting with the device as well. And also from the interviews, we concluded there was a large amount of people who found it more important to have a functional hand, that they're able to achieve all these tasks and do all this dexterous motion rather than having just a solely human hand design. Even if it requires having more fingers, etc., or a less human-like design, the functionality and its overall capability in achieving tasks successfully is more important. So that was kind of the main takeaways we took from this interview, and we will try to implement in future iterations of design, as well as in future goals. From there, we tried to plan out how exactly we want to do this prototype. So based on all this user feedback, how can we make a prototype that users could test and kind of get an evaluation of what our hand would possibly look at as a prototype? So from here, you can kind of see some quick, simple sketches that we did to kind of try to demonstrate ideas. And we originally were planning on just doing kind of like a prototype that we could just ideally give to Brett and test. But later, especially in figuring out how to strap it, was very difficult, and it would end up taking more time than we had available. So the next step was based on a video that we had seen online by Cantalino, of just kind of like adaptive strategies and control that they used over their soft hand, which they did almost like a simple gripper to try to use and manipulate this hand, using just an able-bodied person to open and close a device, which is allowing them to be able to do these grasping techniques. We decided to kind of use a similar approach with our own hand. So we decided that the best possible way to do and achieve this kind of prosthetic prototype, as well as to also kind of make something easy and simple that we could do in a short amount of time, would just be making this able hand prosthetic. So we started off by kind of making a CAD model, the mechanical design, and then we later made the circuit and electrical components before adding the software to be able to control these grasps and do especially the difficult motions like screwing, as well as screwing, twisting motion, and the picking and grasping of objects. We want to be able to control that using this able hand prosthetic prototype. So we first started out by doing the mechanical design. As you saw earlier in the CAD model, we used to have a simple kind of gripping technology. Well, gripping device. Quite simple, almost like you see with the toy grippers that are used to just pick up objects with children. These kind of it's just made so that you can use it, just easily move your hand back and forth to kind of achieve that gripping. Then from there, we also tried to make a circuit. The circuit will just be a simple potentiometer attached basically with the knob in this gripping part. So then when you move it back and forth, it can move the potentiometer value back and forth. And based on this potentiometer value, we will send it back to the hand to control grasp. We also added an LED through a digital pin so you could see kind of how this potentiometer affects the circuit, as well as if it's getting properly sent through. We used an Arduino Nano to send this signal back to the computer so that we could use it. From this video, you can see the success in getting the Arduino Nano to read through the potentiometer value and just control that LED, making it brighter or dimmer based on where the potentiometer is. And then from there, because of the Arduino, it's sending it through the serial port and using data and helping us acquire data that we can use. Kind of seeing like, as it moves up and down, you can see it being plotted in the graph and having values like 241, for example, and the max amount of value that it achieves is about 1,020. And then using this, we can normalize the value between 0 to 1 and use it to control these graphs. As explained kind of earlier when we hard-coded the poses, our motors currently operate by opening and closing a hand based on a value of 0 to 1. So then from there, we'll just multiply the potentiometer value, now normalized to be between 0 and 1, and then multiply it to make these different steps in between the hand, almost staggering the graphs so that you can have more control over an opening and closing position. And then from there, we have this potentiometer value being sent to the Arduino through the serial port. We use ROS2 to have some communication nodes. First, taking in the serial port information using Pipe Serial and making a subscriber node to take this value from the laptop to send it over to another device, which would control the hand. The hand will later have a publisher node from there that is already coded that will take in the value that's sent from the potentiometer and publish that to make it actually mean something and control the motors of the hand. Right now, the code has already been finished with the publisher and subscriber nodes, so the values are being sent over to the other device. What we're still currently working on is completing that final step of having the motors be controlled from there. So then basically after all of this, we had these 3 different things, which is doing the difficult tasks, the interviews, and the prototype, the final prototype. So just to summarize, a lot of the next steps that we aim to complete based off of all this is first off refining our hand to accomplish the task more smoothly and more human-like, especially because as you can kind of see in a lot of the screwing in motion, as well as the grasping, our hand currently is not able to have a super tight and grasp over the pin, as well as to have a tight grasp even while screwing the can. So we want to try to ideally have a tighter grasp on these objects and also just attempt a more wider variety of tasks, even attempting the 3-jaw chuck that current prosthetics are able to achieve very well, and even trying to achieve holding like heavy objects, like more of like a drill, because a lot of prosthetic users want a prosthetic that is able to hold a lot of heavier objects like they encounter, for example, like holding groceries. So if we're able to achieve something like that, that would be amazing and demonstrate our capability as prosthetic. Though this may require refining our current hand design and the way our hand is made to suit these tasks. Because currently right now it's an optimized design that is made for grasping. And if we can adjust and add a wider variety of tasks, we could probably accomplish the screwing motion and picking motion more successfully. We also, for our interviews, we have gotten a wide variety of opinions, especially regarding the customization. That was probably the biggest thing that we received. And we kind of understood that maybe for future directions, we may need to showcase how a lot of our hands differences, because it's soft, it has almost a more fragile look. These offer a lot of advantages in having a wide variety of movements and all these degrees of freedom that the hand is able to achieve all these dexterous tasks. We may want to shift our market to showcase all these advantages that our hand offers from its differences from current prosthetics and even rigid robotic hands that you see. As well as we want to explore how these customization options could play out with our current hand that we're using. And we also want to test a rigid skeleton with our soft hand, which we currently are working on with some collaborations that we have. And we're exploring having a rigid skeleton with a soft skin over it, almost having the best of both worlds of having a rigid design, but still having that softness offered. So we will do some further testing over this with our prosthetic, ideal prosthetic hand. From the prototype, we also just mainly the next step would be to finish that remaining software components to basically, even though right now we're sending the potentiometer value over, we want to complete the final process, which would be having that potentiometer value cause the motion in the hand. So we'll need to have the potentiometer value actually control the motors and adjust the motors accordingly to be able to open and close the hand, for an example. So we need to finish the remaining software components, and then from that we could bring to users to provide an opportunity to test our hand as a prosthetic and collect more feedback off of that so that we can have a bigger idea of, again, the modifications we may need to make in our planning as well as future design that can allow our users to have and make a successful prosthetic that they would want. So overall, that was kind of the whole entire presentation. I hope that kind of gave an idea of a lot of the things I completed this summer through the Robotics Institute Summer Scholars Program, the RIS program. I want to say thank you to the people behind all the RIS program and giving me this amazing opportunity to conduct research this summer and be able to work on all these amazing projects, especially with the prosthetic. It's been so exciting to see all the different innovations that are currently been made and are currently being making with the prosthetic technology. And also this project was partially supported by the NSF Convergence Accelerator Award. So we want to thank them for sponsoring us on this. And to conclude, here are some of the references that I refer and projects that I referred to during the presentation. And thank you so much for your time.